At first glance, science might seem like a chaotic mix of curiosity, creativity, and complex equations, but underneath all the experiments, discoveries, and innovations lies a structured process that helps scientists make sense of the world. This process is known as the scientific method, a step-by-step approach that transforms simple observations into reliable knowledge. Whether someone is studying black holes or bacteria, climate change, or chemical reactions, the scientific method provides a clear path forward. Let's take a step back. What happens when you notice something odd in the world? Say, bread mold growing faster in one cupboard than another. You get curious. That curiosity is the starting point of science. Observation. You observe something unexpected, interesting, or unexplained. And that triggers a question. So what's the next step, you ask? Why is this happening? This is where you define your research question or problem. In this case, why does bread mold grow faster in cupboard A than in cupboard B? Notice that the question is specific and testable. It's something you can investigate, not just wonder about forever. Next comes the hypothesis, an educated guess. A hypothesis isn't a random shot in the dark. It's based on what you already know or suspect. Maybe you think cupboard A is warmer and mold grows faster in heat. So your hypothesis might be, if bread is stored in a warmer cupboard, then mold will grow faster. This is a clear, testable statement. And it points to the next step, experimentation. This is where things get hands-on. You set up an experiment to test your hypothesis. You place identical slices of bread in two cupboards, control other variables like humidity and light, and monitor mold growth over several days. The goal is to isolate one variable, in this case, temperature, and observe its effect. Then comes data collection and analysis. You measure how much mold appears, how fast it grows, maybe even what type it is. You take notes, photographs, or samples, and after gathering your results, you analyze them. Did the warmer cupboard lead to faster mold growth? Do the numbers support your hypothesis? This leads you to your conclusion. If the data supports your hypothesis, great, you've added a piece of knowledge. But even if it doesn't, that's not a failure, it's scientific progress. A disproven hypothesis can still reveal important insights. Maybe humidity or airflow played a role. Maybe you need a better thermometer. Either way, you now have more information than you started with. But science doesn't stop there. A key final step is communication. You share your findings through reports, presentations, papers, or even informal conversations. Other scientists can replicate your experiment, challenge your assumptions, or build on your work. This collaborative cycle is what gives science its power. It's self-correcting and continuously evolving. And perhaps the most important truth of all, the scientific method isn't rigid. It's flexible, iterative, and adaptive. Sometimes a surprising result sends you back to the observation phase. Sometimes a new question emerges before you've even finished analyzing the first. It's more like a spiral than a straight line, constantly building upward toward deeper understanding. So what are the steps of the scientific method? Observation, noticing something, and asking questions. Defining a specific testable problem. Hypothesis, making an informed testable prediction. Experimentation, testing the hypothesis through controlled investigation. Data collection and analysis, gathering and interpreting results. Conclusion, deciding whether the hypothesis was supported. Communication, sharing results so others can verify, learn, and build further. Could a school student use this to test how different music affects plant growth? Absolutely. Could a Nobel Prize winner use the same process to develop a cancer therapy? Yes, they do. The scientific method is universal, and its power lies in its simplicity and adaptability. And perhaps that's the beauty of it. Behind every scientific breakthrough, every vaccine, telescope, or robot lies a humble cycle of asking, testing, and refining, a way of turning curiosity into knowledge and knowledge into change. Observation and questioning. The first step of the scientific method begins with careful observation of the world around us and the identification of phenomena that spark curiosity. Observations lead to the formulation of questions regarding how or why something happens. This step requires an open and inquisitive mind that notes patterns or anomalies in nature. By asking specific, focused questions, scientists lay the groundwork for subsequent investigations. A researcher might notice that certain plants thrive in one area but not another, and then ask what environmental factors are causing this difference in growth. It's like noticing that your car performs better on a smooth road than on a bumpy one, prompting you to question what aspect of the road is affecting its performance. Research and background information. After formulating a question, the next step is to gather existing information and review the scientific literature related to the topic. This research helps to understand what is already known, identify gaps in knowledge, and refine the original question. By studying previous experiments and theories, scientists can build upon established work and avoid duplicating efforts. This background research is essential for creating a solid foundation for the hypothesis. Before testing the effect of a new fertilizer, a scientist reviews previous studies on soil composition and plant growth. It's like reading a recipe before trying to cook a new dish. You need to know what ingredients and techniques have worked before you can make your own improvements. Formulating a hypothesis. With a clear understanding of the background, scientists propose a hypothesis, a testable predictive statement that offers a potential explanation for the observed phenomenon. The hypothesis should be specific and measurable, outlining expected outcomes if the underlying idea is correct. It serves as the guiding focus for the experimental design and subsequent data collection. A well-crafted hypothesis bridges the gap between the initial question and the experimental investigation. Based on observations, a researcher might hypothesize that increasing the amount of sunlight a plant receives will proportionally increase its growth rate. It's like predicting that adding more water to a recipe will make a soup thinner, setting the stage for a controlled test. Designing the experiment. Once the hypothesis is established, scientists design an experiment that can test it under controlled conditions. This involves selecting appropriate variables, establishing control and experimental groups, and determining the methods and materials required. A well-designed experiment minimizes bias and ensures that any observed effects can be attributed to the variable being tested. The detailed planning at this stage is critical for obtaining reliable and reproducible results. To test the effect of sunlight on plant growth, an experiment might involve growing identical plants under different light intensities while keeping water and soil constant. It's like setting up a taste test where each sample is prepared identically except for one varying ingredient, so you can be sure which change causes a difference in flavor. Conducting the experiment and collecting data. In this step, the experiment is executed according to the design and data is collected systematically. Observations, measurements, and recordings are made in a structured and unbiased manner to capture the outcomes accurately. The process often involves multiple trials and careful documentation to ensure that the data are statistically significant. Proper data collection is essential for validating the hypothesis and drawing meaningful conclusions. A scientist measures the height of each plant over a series of days, recording the growth under various light conditions to create a reliable data set. It's like keeping a detailed journal of your cooking experiments, noting the exact amounts and cooking times to see how each variable affects the final taste. Analyzing the data. After data collection, scientists analyze the information using statistical methods and graphical representations to identify patterns or trends. Data analysis helps to determine whether the experimental results support or refute the hypothesis. This step involves calculating averages, variances, and testing for significance to ensure that the findings are robust. A clear interpretation of the data is crucial for understanding the implications of the experiment. Researchers might use statistical tests to compare plant growth under different light conditions, concluding that increased light correlates with faster growth. It's like comparing the results of several taste tests to determine if a change in an ingredient truly made a noticeable difference in the dish. Drawing conclusions. Based on the analysis, scientists draw conclusions about the validity of the hypothesis. They determine whether the data support the original prediction or if the hypothesis needs to be revised. This step also involves considering alternative explanations and assessing the reliability of the experimental design. Conclusions are then integrated into the broader context of existing scientific knowledge. If plants grown under higher light intensity show significantly greater growth, the conclusion may support the hypothesis that sunlight boosts growth while also noting any unexpected findings. It's like finishing a recipe experiment and concluding that the extra water indeed thinned the soup, but perhaps altered the flavor, prompting further refinement. Communicating the results, the next step is to communicate the findings through scientific papers, presentations, and discussions with the research community. Clear communication allows other scientists to evaluate, replicate, and build upon the work. Transparency in methodology and data analysis is essential for peer review and advancing knowledge. This dissemination of results is a cornerstone of scientific progress and collaboration. A scientist writes a detailed journal article describing the experiment, data analysis, and conclusions regarding the effect of sunlight on plant growth. It's like sharing your favorite recipe with friends, explaining every step so that they can recreate the dish and suggest their own improvements, replication, and further inquiry. The final step of the scientific method involves replication of the experiment and further inquiry to refine or expand upon the findings. Replication helps to confirm the reliability of the results and identify any anomalies. New questions often arise from the conclusions, leading to additional experiments and a deeper understanding of the phenomenon. This iterative process is fundamental to the self-correcting nature of science, continually building a more comprehensive body of knowledge. After initial success, other researchers might repeat the plant growth experiment under different environmental conditions or with various plant species to test the universality of the results. It's like having several chefs try out your recipe to see if it works consistently and then making adjustments based on their feedback to perfect the dish.